It's very nice to be back at UCSC, always. Can you hear me well? Good. All right, so I don't know you, and I will try to get to know you during this lecture and later this week. So just so I have a rough idea, can you raise your hand if you are one of the astro students part of the summer school? Okay. All right. And for the others, are you in computer science? Raise your hand if you do. Or physics or astronomy? Okay, good. Just so I have an idea. All right. I'm going to ask you questions during this lecture, and I hope it will be a discussion more than just me talking for an hour and a half. So let's see. Shirley told you about machine learning at a deep level. Today it's going to be very different. I'm going to tell you about data, how to think about data, what are the different types of data, the different flavors, the different techniques that we should think about to analyze these different types of data sets. I'm going to introduce a couple of tools. If you don't understand why first, be patient. You will see why later in the lecture. They will also be useful for the next 2 lectures I will give you in the next 2 days. So first I'll start with a brief overview of data in general. Then I'm going to introduce a couple of tools, and then we will put all of that together. Don't hesitate to interrupt me anytime. All right. Let's see, does this? Okay, so I'm going to talk about information, noise, and structure in data. Great, it's working, but the other way. All right. So this is aimed mainly at people in astronomy, so I'm going to use examples from astronomy. What this is showing here on the y-axis is the number of objects we have in different data sets as a function of time, going from around 2000 to 2025. And so I picked 4 different astronomical surveys. TUMAS, SDSS, the Subaru Sumire survey, which is ongoing, and Euclid space mission. Each of them is observing both sources using imaging and doing some spectroscopy. And as you can see, so the y-axis is in log scale, so we see the exponential growth of the sizes of these data sets as a function of time. Interestingly, there is roughly constant offset between the number of sources we have in imaging data and in spectroscopic survey. It's about 1%. So as one technique improves, the other technique seems to improve also by the same efficiency. All right, so this is talking about data size in astronomy, and as you all know, data sets get always bigger. But there are other interesting properties of data that we should talk about. All right, so what I'm going to do here, I'm going to put basically any data set in this space. The y-axis is about noise. You can think of it as stochasticity or temperature. The x-axis is about complexity, and I will come to that in a second. Or maybe let me say it right away. So there is no definition, generic definition of complexity. Complexity comes in different flavors, and very often complexity has to be thought of apparent complexity. This is what we observe. If you want some proxies for complexity, you can think of it as how many different scales do I have in my data, or what is the description length that I need to describe the data. Okay. Those are 2 possibilities. There is more. And so now I can try to navigate in that space. So if I start at this corner, I have no stochasticity and I have no complexity at all. Okay, so my data set, imagine I have some space, a 2D space like an image, and I have some pixels. Okay, I can put all my pixels on top of each other just to form a point. Okay, that's as simple as I can get. Now I can increase the complexity, and so here I'm going to increase the number of scales I have in the data. Okay, so I go from a point to a segment, right? And still, this is all cold and completely deterministic. I can increase, and I'm going to use the core curve as an example. Now I have several segments, I have more scales in my data, and I can increase, and I can increase, and I can take the limit, and I go to the world of fractals. All right? Okay, so this is all without any noise. Now what I can do, I can go back to the corner here, and I can start to add some noise. And if I do, and now we are in 2 dimensions again, this is what I get. So I start from just a point, and if I add some noise in 2 dimensions, I start to see a Gaussian around it. And if I take the limit, I have an infinite variance, then I have a uniform random distribution, or Poisson distribution. All right? So those are 2 different axes. For the students in astronomy, you probably have a lot of experience trying to do science along the vertical axis here, because in astronomy we have noisy data. It's difficult to collect photons for very faint sources. So very often the source of variance is mostly coming from the vertical axis. Okay, and if you navigate along that axis, you have to deal with the Gaussian distribution almost always. Okay, that's the key that describes what's going on in the data. The story is different if you ride the x-axis. So now, what I can do is to start to add some stochasticity, add some offset in the complexity axis. So if I do this, oops, before that I forgot, those corners have names attached to them. This is the world of Euclid. This is Gauss at the top, and this is Mandelbrot at the bottom right. Okay, you know all of them. Let's continue. So let's start to add some stochasticity. So what I have here is a stochastic fractal. Okay, so it's the same principle as this one, but instead of having this very deterministic way of turning left or right, I add now a random variable. And by doing this, I still have a given recipe to build this object, but it becomes stochastic, and this is what I start to form. Can you recognize this? Does it look like something you know? I can help you by adding this. Tell me. Sorry? Coastlines. Yeah, coastlines. Okay, so this is a way to generate coastlines. As you might know, coastlines do not have a length. Okay, the length of a coastline depends on the size of the ruler you use to measure it. The smaller the ruler, the longer the total length of the coastline. That's a property of fractals. And so this is what we start to form by having a stochastic fractal. Okay, so here the key point is that we are dealing with objects that have higher complexity, and by this here I mean they have lots of scales into them. All right, so I can continue by adding objects from the world. They are simulated or real ones. Okay, and so you recognize lots of familiar things there. And so now so we have, in some sense, those are all stochastic fractals, by the way. And what we see is that a lot of the natural world lives in that space. Okay. And now, as time goes on, we have data that is basically pushing along that direction. Okay, we can collect information for more and more complex systems. And so we are basically riding this axis. This is about machine learning, so I need to talk about cats. And I'm going to put cats as well in that region of the figure. And so now I'm going to ask you why that's the case. So here we are talking about apparent complexity and number of scales, but a cat is a cat. So why would it belong to that region of the figure? And another question also, why? In machine learning, we all often talk about identifying cats in pictures rather than dogs. A cat is much simpler than a dog, first. Okay, do you agree with me that a cat has a scale? Okay, if you talk about dogs, there is much more variance. Okay, some dogs are 10 times bigger than others. Okay, adult dogs. All right, but for cats, that's not the same. A cat is basically big like this, always. Okay, there is much less variance in cats. Okay, it's much better defined. But I'm going to put it in this region of the figure. So why? What makes cats in pictures complex objects? You should tell me. Yes. Yes, that's good. Do we have another? Yes. Okay, but they are, yes. They are. Okay, yes. About, sorry? The, than a dog. I don't know about that, but okay. We had some good ideas here. It's definitely true that yes, the patterns on the fur, the texture of the fur is complex. And going back to just cats having a single size and a single shape, if you want, in 3D, when you see cats in images, they are in all sorts of positions. Okay. If you don't believe me, here is a sample. All right. At the top, we have very common positions in which we see cats. And at the bottom, we have much less common positions, but they do exist. Okay. And if you want to recognize cats in pictures, you have to be able to describe the entire distribution, which is gigantic. Okay, so the configuration space here is huge. Okay, and that is what's going to lead to really high complexity. Okay, so if I want to be able to detect cats in pictures, I need to come up with a way to describe all of this. Okay, and this is a very it's a long tail distribution. So what is shown here is that as soon as you enter this world here, you find these parallel distributions everywhere. The Gaussian is no longer the key distribution. You see these parallel distributions. Okay, and so here the x-axis could be the number of the different positions in which we see cats, and this could be the probability in which we see cats in this position. So there are a few positions in which it's very common to see cats, but then there are many, many, many positions in which we can see them. They are not as common, but they do exist. And if you want to detect cats reliably, you need to be able to encode the entire distribution. And the fraction of area under the curve, you see, that is for the rare events, is actually quite appreciable. Okay, so you need to have this ability if you want to detect cats in pictures, and that's the real challenge. Okay, so even though cats have one scale, one size, they can give rise to a very high apparent complexity. Okay, so some of the statistical tools you learned in your stats classes, usually they tend to be all about writing that direction. Okay, so it's using the Gaussian, the chi-square, and so on. But often you don't learn at your level the tools to be able to write this direction. Okay, and so what I'm going to show you is that one of the key quantity here is entropy. If you know and if you understand entropy, it will be a great help for you to explore this axis. Okay, so one more point about this figure. I didn't say it explicitly, but those are the two sources of variation or variance in your data. Okay, so you can have variance due to noise, and you can have variance due to structure. Okay, in both cases, they increase the variance, or they contribute to the variance. And your goal usually is to get rid of that one and explore this one, because this is the interesting one. Right? But a priori, an algorithm, for example, in general, has no way of knowing which one is going to be the one you are interested in, unless you really teach the algorithm to focus on that one. Okay, and so the statistics are going to be different in each direction. All right. You might also have noticed, you haven't been in the field as long as some of us here have been, but as time goes on, the type of data that we analyze keeps moving to the upper right or to the right of this figure. Okay, I'm going to discuss this more. Your ability to analyze data sets in different coordinates here depends on the tools that you have and depends on the language that you can speak. Okay. If you only know Gaussian distributions, it's going to be very difficult to analyze things like this tree here. Okay. And so often the limitation is not the size of the data, but basically the tools, the ways you have to interact to extract information from the data. All the information is in the fluctuations. The fluctuations are due to either noise or structure, and the whole challenge is to basically extract the one you want. Okay. So, any questions? All right, before I move on, so when you do data analysis, try to remember this figure and try to understand, where is your data set in this space. You can compare that to the data set of one of your colleagues, and that's going to tell you whether you need to use similar tools or not. All right. How do we do science? All right, this is a quote by Gibbs, who tells us that doing theoretical research is to find the point of view from which the subject appears in the greatest simplicity. Okay, so that's what we try to do as scientists. We look at the world, we try to describe it, and we try to come up with a representation that's going to be as simple as possible. All right, and often this is not what many of these modern machine learning techniques do. Okay. So your goal as a scientist is to really end with simplicity. You don't want to end with complexity. Okay, so if all you've done is to train a neural net, the neural net has learned something, but what it has learned lives in some black box with millions of parameters. You have not reached this point. Okay, and so you need to do more, okay, as a scientist. And this is different from what engineers are trying to do. They have very different goals. But as a scientist, your goal is to try to end up with simplicity. So as a function of time, in order to get there, we've used a lot of visual insight. And here I'm talking about centuries. Okay, so for centuries, visual insight has been a key driver when people looked at the world with their own eyes, when they use microscopes or telescopes or all sorts of instruments. Visual insights has been a key to find patterns and to try to make sense of data. And something important that you might not realize is that at the end of the day, when we describe what we see in the world, we use a language, okay? And we use a language of physics and statistics. That's what will end up in your scientific papers, okay? They are written with English and some equations. Those equations typically have several parameters or a dozen parameters, but not millions of parameters, okay? This is not what you write about, and this is not what you talk about, okay? So this is actually a very important key point of the way we do science. So now, as a function of time, we are collecting larger and more complex data sets, and as a result of this, we have some challenges. Visual insight is receding. Okay, this is due to a number of things, but mainly because the size and the dimensionality of the data sets that we have is just much bigger than us, and so we can no longer interact with the data as visually as we used to do a long time ago. Okay, so we now need to interact with the data mathematically, and as we will see, that can be the limitation in extracting information. And when it comes to language, you might not have realized, but this actually can be a limitation. Okay, and so very often in astronomy these days, so there are many cases, we're going to discuss some of them, where the limitation is absolutely not the size of the data or the quality of the data, it's our ability to come up with the right language to extract information. All right, let me give you an example. So you are talking on the phone to a good friend of yours, okay, and you need to describe what you see, okay? So first, this is what you need to describe over the phone, okay, just using English words to your friend, okay? If you have just, if you have a minute or two to do that, I'm sure you will manage. You have to think a little bit maybe, but you will come up with a way to describe this to your friend who is on the other side of the line. Yes? Okay. Now I'm going to show you another simple black and white image, and you need to describe that one to your friend over the phone. Okay, how would you do that? Much harder. Okay, this image is not that more complex, it's black and white. It doesn't have that many scales to it. Okay, but suddenly we no longer have the language, the vocabulary to describe what we see, and we are stuck. Okay, and I'm sure that if we were to do the tests, I do that in class sometimes with students. Half of the students can see the screen, the other half cannot, and they have to write on a piece of paper. They have to describe this, and the other ones have to draw based on the description. It's very interesting to see the results. Okay, and you agree with me that this is really hard, right? Because you don't have the right language. So coming back to this, so there are these two limitations that I think really apply very strongly in astronomy. On one hand, we can no longer see the data in its entirety. We have to interact with it mathematically. And so the limitation is how many tools we know and what these tools can or cannot do. And connected to that, it has to do with the language that we have, which basically sets a limit to what we can do. All right. So, talking about astronomical data, those are examples in 1D and in 2D. We have spectra in 1D, and in 2D we see galaxies. And now what I'm doing here is that I'm writing the complexity axis again, and you can see how these different data objects look like if we increase the number of scales that we allow in the data. All right? So most of data analysis in astronomy is kind of stuck on the left side of this figure. Okay? Because historically, that's where things came from. We've had high-resolution pictures of galaxies for a long time, and we've had this complex spectra for a while. But we haven't had for a while as well the tools to basically extract the information from these kinds of objects. Okay? When we have a blob in 1D or in 2D, we know how to do. We use a Gaussian in 1 or 2D, and we extract the parameters, the mean, and the variance, and we are done. We know that there is nothing left to extract from this kind of data. But as complexity increases, then it's less and less obvious what to do. And as a result, we have a lot of very rich data in astronomy that applies to other fields of science where analysis have not yet extracted all the information that can be extracted. Okay, and this is again a limitation of language, if you want. Now, if we look at, let's look at images, and let's look at even the bigger picture. We have to keep in mind that the range of complexity we have in astronomy is more limited than the full range of complexity we have if we use images of the real world. Okay, and even though there is a wide range of complexity here, okay, it is still more compact. It is narrower than the full range if we include all the images that people use with all these machine learning techniques these days. Okay, and you will agree with me that this is much more reduced than that. Okay, so astronomy, in some sense, is kind of like halfway between these two extremes. And we'll have more discussions about this later in the week. What kind of machine learning tools actually can make a difference in astronomy, knowing that the regime of complexity is not really the same. There's another important consideration with data is what kind of data we want. Okay, so we can get data in different ways. We can have a controlled experiment. Okay, so I have a question. I want to get an answer to that question, and I'm going to build the ideal experiment to answer the question. Ideally, how much information will this experiment produce in the ideal case? Okay, so I have a question, and I want to design the ideal experiment to answer that question. How much information do I need? What would be the ideal answer of the experiment? Yes. Okay. Enough to answer the question. Okay. So, but the minimal answer would be just one bit of information, yes or no. Okay, and we are done. That's the ideal case. And so, when we have a question, and we want to build an experiment to address this question, the experiment will be built in such a way to produce the least amount of data. okay, because you want to be as close as possible to the answer of the question. And so ideally, it would just be a yes or no answer. Okay, and so ideally, the amount of data would just be 1 bit. Okay, and that's, you know, the regime corresponding to, for example, telescope proposals. Okay, you start with a question, you write a proposal to get time on a telescope, and hopefully, you know, you try to convince the TAC that if you are given that data set, you will be able to answer that question. Okay, and so you're trying to design the data collection to focus only on what you need and not get anything else. Right. Now there is the survey mode, which is different. Here we are not starting with a question, survey like the Sloan Digital Sky Survey or the upcoming LSST. We are not starting with a question. We are collecting data in a controlled manner, but not in the same regime as this. We don't want to minimize the amount of information. We want to collect a lot of data, but we want this data to be of the same type, if possible, as stable as possible, as homogeneous, etc. And, you know, those are the surveys that will give us large collections of images and spectra. Okay, but it is restricted. Okay, it's still living within some finite space, which is much, much smaller than this kind of completely open data collection, which is used a lot in the machine learning world. Okay, and so there are different flavors here, especially when it comes to controlling the observing conditions and the systematics and so on. Okay, but so I want you to keep in mind that even though, you know, it looks like there is a lot of variability and complexity in these surveys, you know, these data sets still live in a finite world, much smaller than this kind of world. Okay. All right. Okay, so here is an astronomical image. It's coming from the DECAL survey. The question to you here is this complex? And if so, where is the complexity? Okay, so take a minute to think about it. You can discuss it with your neighbor if you want, or you can just raise your hand if you have some ideas. Let's talk about this. Let's try to understand where it lives in the space I showed you before. Is it complex? Is it not? Discuss with your neighbor and see if you have the same view. You know, is it complex or not? If it's complex, where is the complexity? Thank you, Xavier. Now they are very talkative.
37 December. Oh, okay, no. Very coincidental. It's 9:37 on my clock.
Yes, I came from a ship. All right, let's have a poll. So if you think there is some complexity, if you think this is complex, raise your hand. Don't be shy. Okay, if you think it's not complex, raise your hand. And don't be shy at all, even if you are the minority. Okay, so let's start. So why do some of you think it is not complex? It's medium complex. Okay, let's see.
Because it depends sort of on what your problem is. If your problem is to like separate stars and galaxies, then it's not a complex, not a complex image, or it's not a complex system or problem. But if your question is like how like a detailed like a deconstruction of like different classes of galaxy or different classes of star using splitting color and other information, then it becomes a complex problem.
Okay. Any other view? Those are all good things, yes? Okay. Okay. Mm-hmm. Okay. All right. So the question is, what do we need to describe what we see? Okay. Do we have the right language? So most of what we are seeing here are galaxies, and there are some stars as well. And of course, we can have different questions, different scientific questions here. But first, let's try to just describe what we see, and let's see how far we can go with, the tools we have to describe and the language we have to describe what we see. This is, this is not very high-res in the sense that we don't resolve very much many of the galaxies. Okay, it's not. Those are not very nearby objects. They're at cosmological distances. And because of seeing, due to the atmosphere of the Earth, basically we end up with a collection of blobs. Okay, those are blobs in 2D. There is not that much shape information, right? And so if we have a blob, okay, maybe let's see, where are we going to be in that axis? I mean, what kind of objects do we have? Okay, we tend to be on the left side of this. Okay, so if we have a blob, we can basically describe it using Gaussians and moments. Okay, so what I can do here, I can describe each blob. Maybe I will use the board. That's probably fine for now. Okay, so in 2 dimensions. Okay, so if I have something like this, that's my blob. I can describe it. So I have some intensity as a function of x and y. And so I can take the moments of this distribution. So this is a distribution of intensity as a function of spatial coordinates. What I can do, I can integrate this. So if I integrate dx dy of this distribution, and let's make it, I'm going to call that, let's see what's going to be the best. Okay, I'm going to call that I prime of x and y, okay? And I'm going to get the total intensity, okay? And so here this is normalized, this is per unit area, okay, to make it simple. Now if I take the first order moment, what do I get? Okay, so the first order moment is going to be of this. And I'm going to normalize this by I0. Okay, so then I'm going to get the position x. I do the same for y. I'm going to get the center x and y. Now I'm going to look at the second order moment. Okay, so I'm going to integrate this using x minus x bar. First, I'm going to do this square. What do I get? going to get the variance in the x direction. I do the same with y. I get the variance in the y direction. And I can do across x and y, and I get the covariance. Okay. What are the other, so what is this? Okay, so now if I just take the square root to have a length, okay, so what I've done here, I have the total intensity of my object. Then I have the center, okay, so this is going to be the barycenter of light. That's what I have computed here. And now I'm going to the second order moments. And so now this is going to tell me what is the sigma in that direction for x and the sigma in that direction for y. Okay, and so by doing this, I'm representing, so this is a Taylor expansion if you want. Okay, so I'm expanding, I'm looking at higher and higher order moments. I'm describing my object as basically an ellipse. Okay, so this, I'm approximating this object by this kind of ellipse here. Okay. All right. And so what do I need at the end to describe this object, which had a more complex shape at the beginning? I just need a couple of numbers. Okay, and those numbers are just coming from the moment expansions of my light distribution. All right. And so now just using these 6 numbers, I can basically reproduce something that's going to be like this, that will be at the right position, with the right size, with the right orientation, with the right brightness. Okay, it's not all the information, but probably I have captured a lot of that information, especially because we don't see very small scale information in this image. Okay, if you think of it in terms of scales, there are not that many scales in this image. All right. So what I can do, I can detect all the sources in my image. I can compute the moments. I can extract the parameters. So what I get is a catalog of objects and properties. And what people do, they are going to extract 10 to 20 parameters per object if you want to describe the colors and all sorts of extra information. And just out of these objects, they can resimulate that image, right? You agree with me that I have all the information there to recreate my own image, not based on the pixels, but just based on the parameters that I have extracted. Okay, so one can do that, and this is what one can get. Whoops. So this is the original image, and now this is the simulated image. I'll show you again. This is the data, and now this is the model. And the model is just using this moment expansion and just using those numbers. Okay, it's more than 6 numbers. They are using a bit more than 10, but you get the idea. Okay, so originally I have an image with many pixels. Okay, I don't remember exactly, tens of millions. But I can end up with a catalog, and the catalog allows me to create this image, but the catalog is much, much, much smaller in terms of the number of parameters. Okay, so I've been able to extract all this information in a very efficient way. Okay, and the reason is that what I have here is a collection of blobs. And if I have blobs, basically that's the English word to say that I have second order type objects. Okay, I can describe them with 2D Gaussians. A Gaussian is a second order moment of my light distribution for every galaxy. Okay, so the complexity of this image is not really in the whole distribution of blobs that we see. Okay, to convince you that the model is a good representation, I can also look at the residuals. So I can do data minus model, and this is what one gets. Okay, you see that most of the objects are gone. We see the black background with some noise. For some of the brightest objects, we see that having just 10 parameters to describe the objects is not enough. Okay, so for those guys, we will need more. Okay, this is because the light distribution is not just a Gaussian, but it has some different shape, and so we would have to go to higher orders to capture that. But again, basically there is not much information left. Okay, so all that information has gone from the pixels to the catalogs. Okay, because we have the right language to describe this. Okay, so having done this, we have done a huge dimensionality reduction. Okay, because we have the right tools to do that. We heard interesting comments also about correlations between colors and clustering, etc. So this has not been captured by this. Okay, this is in addition. And when it comes to that, then yes, there might be some complexity into it. Okay, so if we go back here, there are all sorts. If you don't treat this as a random distribution of points, but if you ask questions about spatial correlations and involving colors, then things can become more involved. And perhaps there is some complexity there, but that needs to be studied. Okay, so this is very powerful, and this is done all the time in astronomy. So the game very often is to try to go from a pixel-based space to an object-based space. Okay, so here we have a catalog, and in the catalog you will find brightness, position, size, ellipticity. Those parameters are exactly the numbers that I derived on the board. Okay. We can do that for all the filters we have. And so we end up having about 10 to 20 numbers to represent each source we have in the field. Okay, and if those are, at high enough redshifts, we don't have much high spatial resolution for them. That's easy enough. We have extracted all the information object per object. Yes?
So it seems like your definition of complexity somewhat depends on the accuracy you want, because then I could have 40 parameters and get the reconstruct data is more accurate.
Yeah, that's right.
That was the accuracy I desired, then the complexity is greater.
Yes, so this is an example where you can increase the number, you can increase the expansion, and you can get more and more accurate. Okay? So here, if we use only 10 to 20 numbers, okay, you can describe 99% of the variance in this image. Okay? And if you want to go beyond 99%, then yes, you can increase the expansion. You can push the expansion, and then you will get 99 point something. You're completely right. But this is because you can use this Taylor expansion. There are cases where you cannot use that. I'm going to show you this. I think it's coming up next almost, so just stay tuned. So for this case, okay, where we have the data, the model, and the residuals, we have been able to use that language to extract the information. And when we can do that, then life is wonderful. Okay, we detect objects, we put the information into catalogs, and then they become searchable. Okay, that's a very important step. You might not realize that, but that's a key. Okay, as soon as it's searchable, you can do all sorts of analysis in a very simple manner. You don't have to go and query, many billions of pixels. So everything is fast and everything is under your control here. And you can look at the statistics of colors, you can look at correlation functions spatially, etc., etc. And you can directly, you have a very direct way to compare models to observations. But that is not always the case. Okay? Now, if we look at images like this, what would you do to extract the information? Okay, so these images are similar, okay, and compared to the big image I showed you at the beginning, this will be order, I don't know, 10 million pixels. Tell me what you are. So the question to you, is there some complexity here? Does anyone think there is not much complexity here? Nobody. Okay, why? Maybe it's because you don't have the right language to extract the information. Okay, the moment-based approach that I used here is not going to take you very far here, and you can try to expand to higher and higher order moments. The gain with which you will be able to describe the variance will be very slow and very unstable, actually. So we have a lot of data like this in astronomy, but this kind of images, they do not end up in the same way in databases. Okay, so the information contained in these images does not end up in databases, and therefore it is not searchable. And therefore people cannot do all the types of analysis that they do on their stars and galaxies with this kind of distributions. Okay. All right, let's continue. Spectra. So spectra might look complex as well if you don't know about them. This is a collection of spectra of galaxies, and we have a star. If you don't know anything about them, this might look complex. To some extent because you don't know what is noise and what is actual structure in the data, and you don't understand the dimensionality of the population. You know, do we have different populations? How much variation per population, etc. So there is some apparent complexity here, especially, you know, when you start in astronomy, you see the spectra, they are hard to interpret because you don't have the right language. But it turns out that for stars and galaxies, we do have physical models that allow us to describe this spectra. And so the red line that you see here, that's a best fit model which is motivated by physics to this spectrum. Okay, and of course the model is informed, so the model knows what kind of fluctuations are intrinsic and due to physics and what kind of fluctuations are just due to noise. All right. So in cases like this, there might be some apparent complexity, but the more you know about these beasts, the better you understand them. You can use physics, you can use a model to reduce the complexity, and you can do the same job. You can go from pixels to object detection, feature, object or feature detection, parameter estimation, etc. And you can extract the information, the relevant physical information from the spectra. You can put that into a catalog or a database, and you can search and you can do the usual analysis. Okay. At the end of the day, for objects like this, because they actually come from simple physical models without that much variation at the end, if I take spectra of 1 million luminous red galaxies from SDSS, so this kind of spectra, okay, we can observe them at different redshifts, but if I put them meaningfully on one scale, this is what I observe. Okay, so this is real data. Those are the same spectra as what I showed before. This is wavelengths. And every row here is one or an average of several spectra. Okay, and so what you see spectra evolving as a function of redshift. So now the y-axis becomes redshift. And the lines that you see are the absorption lines in the spectra, the messy absorption lines that you saw here. But now if we put many spectra on top of each other, we can see that they all look the same. And the only thing you see here is the effect of redshift. Okay, and for the astronomers in the room, this is the 4,000 angstrom break of luminous red galaxies. A very useful feature if you want to do redshift estimation using photometry. And this is being redshifted as you go up in this space. All right, so this is something that we understand well. We understand the physics, and we know how to go from physics to observables, and therefore we can order the data, reduce the complexity, the apparent complexity, and at the end of the day, it becomes very simple. Okay, I have about 1 million spectra here, and as you can see, it's a simple story. Okay, but in order to do that, I had to go through this step. Okay, the step of building a physical model that is going to tell me what fluctuations are due to physics and what fluctuations are not. This is another example with star-forming galaxies. It's the same story, just to show you that lots of features then align, and you see that the story is quite simple. By doing this kind of operations also, and putting several spectra per row, we do a lot of averaging, and the averaging removes the noise. Okay. All right. This is not always the case. Now, if we talk about quasars, for example, we do not have physical models for quasar spectra. This has been missing after many, many years of collecting data of quasar spectra. If you query the Sloan database, you can look at spectra of stars or galaxies, and at the same time as you download the spectrum, you can also download the best fit physical model for the spectrum. You can do that for galaxies and stars, but you cannot do that for quasars. Those models do not exist yet. Okay, so there is a lot of variability in quasar spectra that is not described by understood physical models yet. So there is still some apparent complexity there, and perhaps you will be the ones coming up with those models to reduce the complexity and make sense out of this kind of data. All right, so the summary is that we have these two different regimes. On the left, at low apparent complexity, everything is nice because we can go from pixels to catalogs. Okay? By having done that, we basically have used a language to do dimensionality reduction, reduce the complexity, and we can do all sorts of analysis very easily. But when we're on that side of the axis, then we cannot do that. Okay, and I will show you during these few lectures, how to use some recent tools to basically navigate in that space. But that's the frontier. And here the frontier is not about the size of the data set. It's just about the complexity of the data. As a result of this, there are lots of gems and very interesting objects living in that space that astronomers have not found. Okay. Sometimes these interesting objects were found by the public. Those are two examples in astronomy. The first one is an interesting green nebula which was seen in SDSS images back in 2007. It was not discovered by a professional astronomer, but by a school teacher who was looking at images as part of the Galaxy Zoo project. This is a very interesting object that triggered HSC observations and a number of papers. But because this kind of objects does not do very well when you do this kind of descriptions, okay, it was not spotted by astronomers as something. Especially it was discarded as something that could not be described very well, as often as people say, just junk. Okay, but junk means that you cannot describe what you see often in astronomy. And in these piles of junk, there can be some very interesting objects. This is another example. I'm sure you have heard of this one. This is a very intriguing transit curve measured by the Kepler satellite. It was discovered initially by citizen scientists. So what you see here is the flux, the brightness of a star as a function of time, and we have these huge dips that have occurred a number of times with a very large amplitude. One of them is about 15%. Okay, so 15% of the area of the star has suddenly been obscured by something, and then it goes back to its normal level. So this is a very, very interesting object, but it was discarded by the Kepler pipeline because it was too unusual. Okay. All right. Okay, so things we can do well in astronomy, we can extract, we can basically, we do very well when we have blobs in 1D, blobs in 2D, when we can use Gaussian distributions or polynomial expansions to describe what we see. What we cannot do well is when complexity arises and we no longer have, when this language here is no longer the one that allows us to describe what we see. There are lots of interesting rare objects living in this space that were discovered by non-astronomers, non-professional astronomers, which is showing that we as a community are not using all the tools we should be using. And I bet that there is more to discover that we haven't yet seen. All right. Okay. What we cannot do at all, we will talk more about this soon, but are there ways to automatically find structure, meaning in arbitrary data sets when complexity is very high? And can we find very unusual and very complex objects? Okay, so this is going to end the very first part of my lecture, okay? And the goal here was to basically give you a tour of different types of data, okay? Show you that data size is not really the limitation these days. People spend many years talking about having more and more data, but now that's not the limitation. And one frontier that we have, especially in astronomy, is our ability to deal with complexity. Okay, so as time goes on, we are moving in this direction, and we need tools to deal with this complexity. Are there any questions? Okay, so let's see what we can do. Oops. If we want to move along that direction. So do you know what is the most cited paper in mathematics? That should be a very useful paper, no? Yes? That's the problem. I was not supposed to skip that fast. Yes. So here it is. Okay, this is Shannon's theory of communication. It was published first in 1948, and after some discussions with one of his colleague or friends, he actually updated it 1 year later. The title changed from a mathematical theory to the mathematical theory of communication. Keep that in mind one day if you write a really good paper. Okay, so this is a theory that tells us about how to communicate information, how to quantify and communicate information. And this is very important because this is what we end up doing when we do data analysis. Okay, we want some communication of information from the data to us. Okay, and so it's useful to be able to quantify this and manipulate this information. All right, so let's look at English first. What I have here are all the letters in the alphabet and the space. And using the frequently asked questions manual for Linux, Tim McKay did this and computed the probability, measured the probability for each symbol to appear. Okay, so you can see those probabilities. They span large dynamic range, and therefore if I want to visualize them, it's better not to use just one dimension but two. Okay, and that's what these areas here, these squares do. Okay, so they are proportional to the probability for each letter to appear. You can see that, you can see that Z has a very low probability, the space has a huge one, etc. Now what we want here is to come up with a measure, an estimate of the amount of information we have when we have a random process. Okay, so we can have a random process that generates letters. You can see text as being such a process. Okay, we are going to generate letters. It's not completely random, but there is plenty of randomness in it from an external point of view, and let's see how we can quantify this. All right, so that's what Shannon did. He asked the question, okay, I would like to create an information measure, I of P, of a process, and we want it to have the following properties. Okay, it has to be a non-negative quantity, okay, because negative information doesn't sound so good at the beginning. If an event is going to occur with a probability 1, we are not going to get any information from it. Okay. If two independent events occur, then the information we will have by observing the two, we want it to be the sum of the information we have for the first one and the information we have for the second one. Right? And the last one, we want our information measure to be continuous and monotonic in the probability. Okay, so those look like reasonable requirements for a definition of information. And as a result of this, there is one answer. Okay, one function only satisfies this criteria, and this is the following. Okay, so the information corresponding to a probability density distribution P, to an event with a probability P, is the log of 1 over P. Okay, so this is the definition of Shannon information. Okay, and it's the information content of an outcome X that's coming from a probability distribution function. If we use log in base 2, then our information content is going to be in bits. All right, if we use a natural logarithm, does anyone know the unit of the information? It's called the NAT, N-A-T. All right, so now that we have this measure of information, let's apply it to our list of symbols. So this is, again, the alphabet in English. For English text, I just compute log of 1 over P, and now I get the information in bits for each symbol. Okay, and because we have taken a log, you've seen that the dynamic range has shrunk. All right. Now, I'm in a position to describe or to introduce the entropy of this process. So the entropy is simply going to be the average information. Okay, so H is the information content. I'll go back to show you. It is here, okay? H is just log 1 over P. So when something is not highly probable, then the information content is high, and when it is very probable, it's low. Okay. So this is the information pair symbol, and now the entropy is just the average of all the information. Okay. Now every symbol is coming with a given information H, but every symbol comes with a different probability. Okay, so some symbols will come more frequently than others. So if we want to expand this expectation value for H, this is what we get. Okay, so if you remember, H is log 1 over P. Now we need to take an average, but that's a weighted average because some symbols appear more often than others. Okay, so this is now Shannon's entropy for the process. If we use log base 2, we'll have an entropy in bits. If it's a natural log, it will be in nats. Okay, so it's going to be a measure of the average uncertainty of my random variable. All right, so we can do that for English. I can combine all of this. I can take my weighted average. And what I find is that in English, the entropy per symbol is about 4 bits. Okay, so this means that if I have some texts, it can be very long. I want to know how many bits I need to encode this text in a file. I just have to look at how many symbols I have, and I know that on average I can encode that with about 4 bits per character. Okay? Let's look at some examples. Okay, now first, okay, those are different ways of generating texts. The first one is completely random. This is the 0th order approximation. Okay, so I just pick out some letters randomly in the alphabet, and I get this. Okay, I can start to add some correlations, and I can look at pairwise correlations between consecutive letters. I can add that information in it, and I can start to build this. I can add second order information, and I build this, and this is the third order, etc. And as you can see, this starts to look more and more like English. Okay. All right. You can even see, words you can almost recognize. Now let's just focus on the first line of each sequence, and I have a question for you. Which of them contains the most information? Okay, you can discuss that with your neighbor now and see if you agree. Okay, which of these 4 realizations has the highest information content? All right. Okay. Raise your hand if you think it's the first one. Okay. Raise your hand if you think it's the second one. Okay. Raise your hand if you think it's the last one. Okay. So it's half and half. All right. So as we go down this list, okay, things become more familiar. And if I show you this, you can see the end here, you can see the space, you can see an O, and I ask you what's the next letter, many of you might say it's going to be an F. Right? If I mask some letters here and ask you to guess which letters they are, you will be right much more often here than there. Okay? So if you can predict things, okay, it means that there is less information. Okay? And so there is actually more information in the one at the top, okay? Because everything here is completely random, therefore you cannot predict the next outcome, therefore it has the highest entropy and the highest information content. Okay, so here information, the way it's defined by Shannon, is a little bit different from the way you think about it in English. It's the amount of surprise, the amount of uncertainty. okay, how much you are going to learn. If you have a word like this, and I mask some letters, then now I reveal those letters to you, you have not learned much compared to revealing letters up there, where you had no idea of which letters were there at the beginning. So there is more information when entropy is high, and you can carry more information when you have a process that is unconstrained. All right. Let's see. Okay, so let's look at this case. Okay, we have a random variable with a uniform distribution over 32 outcomes with equal probability. Okay. How many bits of information, how many bits do you need to encode the outcomes? Okay, so we have 32 possibilities, and we want to use bits, so zeros and ones, to label each outcome. How many bits do you need? And I can help you. This is power of 2. Okay, so if you do 2 to the power of 5, you get there. Okay, if you compute the entropy of such a process, you just do the usual minus p log p. You use log base 2. And what you find is that in this case, you will simply need 5 bits to encode each of the outcomes, each of the 32 outcomes. Okay, so you can label each of the 32 outcomes using 5 bits, okay, zeros and ones. And you will do that, and that will be optimal. Okay? So for a flat distribution, okay, or a random distribution, the entropy is just the log of the size of the alphabet. All right? Now, if we have some correlations, if it is not a flat distribution, then the entropy is going to decrease. Okay, and that's what happened with the lines of text. Okay, there is more entropy at the top and less entropy at the bottom because we start to add some correlations here. We have a way to predict what the next outcome is going to be. All right. So now let's look at a more complicated case. Okay, so now this is a horse race. That horse race has 8 horses. They have a different chance of winning, and the chances are written like this. Okay, one is really good, is winning half of the time. Another one is winning a quarter of the time, etc. And so now we are going to have lots of races with those 8 horses. Okay, and each time there is a race, there is a winner. We are going to encode which of the 8 horses has won. Okay, and the question is, now imagine we have many, many races. In the infinite limit, how should we encode the winner, knowing that some of them are going to win more than others? Okay, so we have 8 horses. If we want to encode 8 objects, we can only use 3 bits. Okay, but some of them are going to win much more often than others. So if we do that, if we give the same number of bits to all the horses, that is not going to be efficient. So how many bits do I need to encode the outcomes of these races? This is going to be given to us by the entropy of the process. And the entropy of the process here, okay, you do your minus p log p, and what you find is 2 bits. Okay, so on average, the entropy is an average. On average, you only need 2 bits, okay? So 0, 0, 0, 1, 1, 0, etc. Yes, to encode the winner. Okay, yes? One of the horses is, sorry? It should be 116. Oh, sorry, that's 116. Yes, not, yes, you're right. Oh, actually, even the one is missing. Yeah, I missed the 116. Yes, good eye. Okay. All right, and so how am I going to do this? Okay, so the idea is to encode, maybe I have it on the next slide, exactly, okay? So I can encode the horses like this, okay? For the one that comes, that wins the most frequently, I can just have 0. For the next one, I can have 1, 0. For the next one, I can continue to expand this. All right? Of course, for those that win 1 out of 64, I need a long string of bits. Okay, but I'm not going to use this very often. And on average, if I combine everything, on average, I only need to transmit 2 bits. All right? Yes? No, you cannot, no. If it's a flat distribution, as we saw previously, you need, in this case, you need 5 bits. You have 32 outcomes. Each time you want to label the one that is coming out, you will need 5 bits here.
Yeah, but I can convert the 1 to 32 into binary, and then I effectively only need 2 bits.
I think what you're trying to say is that you can use bits always, yes. And that's true. But how many bits? How much information do you need to address one object into a collection? That's the length. And that's, on average, that's going to be your entropy. Okay. All right, and so by the way, an interesting comment here, when you have a flat distribution, the entropy is the depth of the binary tree that's going to encode your distribution. Okay, so I can have a binary tree. Okay, at the end, I will have 32 outcomes. The number of layers of my tree is the log of the number of outcomes. All right. We are all good with this, and I'm going to skip this. All right. Okay. So now you know about entropy. I'm going to tell you about Lagrange multipliers. Can you raise your hand if you know about Lagrange multipliers? Okay. Good. So half of you do not know. I can send someone to the board to explain Lagrange multipliers, or should I do it myself? Okay. All right. Do this here. Okay, so imagine I start at some position here. So this is a start, and I want to end here. Okay, if I don't have any constraints, what's the shortest path to get there? It's the straight line. But now, before going to the endpoints, I need to, let me make a more complicated case, I need to touch the river. And this is how the river goes. Okay, so now that's not obvious at all. Okay, so I want to go from start to end with the shortest distance, but I want to touch the river on my way. Okay, so the trajectory that's the solution of this problem is not as obvious. And I can get it using Lagrange multipliers. Okay, so I can write this. I'm going to, let's see if that's work. Yes. Okay, so the way I can do this, I can say that I have some function f, which is the total distance. Okay, so basically we will want to do something like this. And we are going to have a point P here. And so the whole goal is to find at which coordinate here I'm going to intersect the river. Okay, so f is my trajectory, my total distance. It's going to be a function of p. I don't know what p is at the beginning. Okay. And I'm going to have an equation for the river, okay, which is going to be described by g of some variable x. Okay, so this is an equation that describes the location of the river. And so what I want is to touch the river at some point P. So what does it mean to touch? What does it mean when two curves touch each other? Okay, so if I have one curve here, okay, I can have another curve that touches this curve like this. Okay, that's one possibility. This is another one. Okay, and this is another one. Do you agree? Okay, they all touch each other. Those are all possible solutions of the problem. They have one thing in common. Okay, so it's that they have the same tangent exactly at this position. Okay, and so this is going to be described by the derivative, okay, or the gradient of these curves, which will have different lengths depending on the curvature of the curve that I use. Okay, so we know one thing is that the gradients will be parallel to each other, but we don't know the magnitude, okay, of these gradients. Okay, so what I have here is that I have some gradient f. The gradient of f is going to be parallel to the gradient of g up to some normalizing coefficient, and that is my Lagrange multiplier lambda. All right, so having said that, we know that if we want to solve this problem, we have to include a new variable lambda, okay, which is going to describe, basically in this case, the radius of curvature of the curve, and a priori we don't know what that is. So we have to solve for this as well. Okay, so we have two unknowns, if you want. One is going to be the point at which we will touch, and the other one is going to be the curvature. All right, we can solve for this, okay. So we have the gradient of f at p is going to be lambda times the gradient of g. Okay, and we also know that g of p equals 0. Okay, that is the equation that defines the river, that defines my constraint. Okay, so what I'm trying to do here, I want to minimize f, okay, the total distance, given a constraint g. Okay, so I want to minimize something, but I have a constraint. Okay, so this is a very generic problem in science and engineering, and one way to address it is to use Lagrange multipliers. Lagrange multipliers will tell you that you want to find the solution, basically the point p, which will minimize and satisfy the constraint. But you know that you will be able to get there with different curvatures, and you don't know which one a priori, so you need to add a new variable if you want to solve this system. Okay, and once you have this is a system of equations that you can solve. You have as many unknowns as equations. Okay, we have two unknowns, we have p and lambda, and we have two equations. So we can solve for this. All right, that's the technique of Lagrange multipliers. We are going to use this soon. Let's see. Okay. All right. Now that you have some tools in hand, let's try to do a couple of interesting things with them. Let's talk about believing and guessing. Okay, this is a situation in which you are very often, you need to make a decision about something, but you do not have all the information about it. Okay, so you need to describe the state of knowledge about a system. You don't have all the information, and this is about believing. Okay, this is your belief, this is your best guess, and that's what you do when you don't have all the information in hand. Okay. There are lots of Bayesian statistics behind this, and I guess David will talk about this soon. I'm going to touch on one concept that's going to be very useful. Okay, so let's start with this exercise. And actually, the singular is dice. Is that one die, two dice?
Singular die.
Die, okay, thank you. So that's correct. Okay, so I have a die, and I toss it many times. And I tell you that the average that I get is 3.5. Okay. What can you tell me about this die? Okay, so the average of all the outcomes is 3.5. You can think about it. You can just compute tiny little sum and a division. And you tell me something about this die. Yes. Yeah, it seems to be a normal die, right? Equal probability for all the outcomes. You have, 6 outcomes. If it's a standard die, on average, you'll get 3.5. Okay. Now, and we have another system. We have a die, but now the average is 4.5, not 3.5. What can you tell me about this die. And so what I want you to tell me the probability pi of every number. Okay, what would be your best guess for the probability of each outcome of this die? The only thing you know is that the average is 4.5. Okay? So in the previous case, we assigned the same probability to all outcomes. Okay, 1/6. But now it's different. Okay. What can you tell me about the different probabilities? You can set some probabilities to be 0. Okay, so let's see. We are going to push this very far. If I can have some extra minutes.
Sure.
Okay, if David doesn't mind. Okay. Let's go.
Just so we're clear, we'll have a break for a while, and then Dave will start at 11.
Yeah. Okay. Oh, okay, good. All right, so what do we know about this die? Okay, we know that on average we get 4.5, and if I write it mathematically, this is what I have. Okay, for all the outcomes, we have 6 possible outcomes. I need to normalize my probability to 1, and I know that the average is 4.5. And so we had one possible scenario, and it's not very different from the proposal 1 that I have here for you. Okay, so what do you think if I tell you that I've tossed this die many times, I get an average of 4.5? Do you think this is a reasonable model for my die? You don't seem to be very convinced. Okay. Common sense tells us this is not reasonable. Okay, I don't really know what kind of die would have 0 probability. This is basically a coin. Okay. It's not a die. All right. So it's not a reasonable assignment. Let's try another one. Okay, so now I have more sides to it. Is it better? Yes, but you don't seem to be convinced, right? Okay. So let's continue. Let's see what I have here. Okay, so I have a new proposal for you. Okay, now let's stop having those numbers set to 0. So this is one that works. Okay, so I have one number that's much more likely than the others. Do you think that this is the best guess for the die? Is that the most likely? Would that be your best guess, or are there other possibilities? Who doesn't like this one? Okay, why?
Too much for probability estimate.
Yeah, too much given to the number 6. 6 has nothing special, right, in that series? Okay, so it has too much, there's too much emphasis on the 6, so it's a bit too special in a sense. Okay, so that's what this is. This says that there is an exceptional treatment for n equals 6. Okay, so let's change that. What about this one? Now, all the numbers have a different probability. Do you like this one? No, some people do not like it. Why? You prefer the other one, but so what's wrong with this one? Yes. Yeah, so you know that you need more weight on the right if you want an average of 4.5. Okay, the question is how should we distribute the weights? Let's just think about an abstract die. Okay, I mean it's abstract enough, but so that's not an issue, but yeah, yes.
It seems quite arbitrary.
Okay.
You just sort of picked which ones had which probabilities.
Okay, that's right. Do you agree? This is a little bit arbitrary, right? It feels arbitrary, yes.
I'm expecting the probability to peak around 4.5.
But to peak around 4.5? Near.
Closer.
Okay, we have a different view, but okay. Okay, so we heard that this feels too arbitrary, and I completely agree. Yes.
One proposal would be that a mean distribution that is closest to uniform, and that our means is mean, its average for.
And so how would it look like?
I don't know how it looks like.
Okay, but what do you like about, when you say this, you're actually very close to saying one concept that many of you have in your head already, but you haven't expressed it. Someone said this is too arbitrary, and you are saying you want to be as close as possible to the uniform distribution. Yes?
I think it would almost be like a step, like upwards. So if one face is particularly, if one face of the dice is particularly heavy, like a loaded dice, then that side is going to be most likely to be the bottom. So if it's a one, if that side happens to be one, then six is the most, then six, which is the opposite side, is one.
Okay, but let's come back to the beginning of your answer. You would like something that's more like, that's smoother, maybe. Okay, something that is less arbitrary, right? Wait, we are not there. Okay, so I'm still asking you. I mean, can someone show me the shape of this curve? Okay, what would be the most likely curve? Okay, that's the question. All right, so this one feels like there is some uneven treatment, right? It's too arbitrary, as we heard. So let's try to deal with this. Maybe what we want is to add one criterion here. It's the concept of smoothness. Okay, we want this distribution to be smooth. Otherwise, it's not, it's too arbitrary, right? If it is smooth, then we have equal treatment to all the numbers. Still putting more weight on the right than the left, but we want to do that in a smooth manner. It will be less arbitrary, right? So we can do this. And for example, I can use a function pi, which is a times I, okay, or a minus 1 times I. And I get something like this. Do you like this one better? Yes, some people do. Okay. Yes. No. We don't. It can be any die you want. Yes. But yeah. And I know you can take that into account, but yes, it's not that advanced. Okay. It turns out that with this kind of function here, you cannot go as high as you want for the mean. Okay. There's a limit to as high you can get, okay, because you are constrained by this functional form and the fact that your probabilities have to sum up to 1.
But if 4.5 is your target, then that isn't good enough, right?
It is not with this one. You need to go higher up.
It has to be more heavy on the 6 side?
On everything, yes. Okay. So what you can do here, okay, you can actually you can add, let's see, okay. All right, so I'm showing you too many things at the same time here. Oops. Okay, so now let's use this one. Okay, so we have smoothness, and now we need to change the first proposal, and so let's simply use AI plus B. Okay, something very simple. And if I use AI plus B, okay, I can solve this, and I can find a solution for a mean of 4.5. Okay, and so I can have all the weights. This is what is shown here. That would be the distribution of the weights, and that can give me a mean of 4.5. Okay, and we are happy, maybe. But now if we look a little bit deeper at this, we realize, and I have 2 slides, but I don't have time to go over it, just to solve the equations. If you solve these equations, you realize that you can find a solution of 4.5, but you cannot find a solution of 4.6, okay? This is ruled out. And the reason is that if you start to, if you want more weight on the right, you still need to have the sum of the probabilities being 1. You need to have negative values on the left. Okay, and you don't have negative probabilities. Okay, so this proposal that works for 4.5, it looks fine, but if we look deeper at it, it's also arbitrary because it can do 4.5, but it cannot do any value greater than 4.5. Now, if I do this experiment and I tell you that the mean is 4.6, you can no longer use that one. That doesn't work because you have to tilt this so much that you start to have negative probabilities. Okay? So even this proposal here has some arbitrariness to it. Okay? So if I'm asking you for your best guess, okay, this is probably not, that would not be my best guess, okay, because I don't want my best guess to work for 4.5, but not to work for 4.6. I want something that is more generic. Okay? Surprising how far we can push. Just an example with the die. So this is not the most probable distribution for my die. Okay? And the only thing I know here about this is that the sum of all the probabilities is 1, and that the mean is some number. It can be 4.5 or maybe 4.6. So how are we going to do this? Okay? So we know that this does not work. So how can I change this curve to make it work for any value of the average? 4.6, 4.7, or anything. How should the curve be? Okay, so we need to add some curvature. We know that the solution to this problem is not a straight line. Okay, and so basically this is the generic answer to the problem. Okay, we need to have some curvature. What kind of curvature? I don't know yet. This is as far as we can push this exercise qualitatively. Okay, but we can now push it quantitatively. Okay, and how can we do this? When we've gone through the different proposals, I've asked you if you like them or not. Okay, and each time there was something about, there was some level of arbitrariness. You didn't like to put all the weight on the 6. You didn't like to have, something that was not smooth, etc., etc. And so there are certain properties of the answer that you want that were not stated in the problem, but you want them, right? The last answer I showed you feels better than the others. It's the most generic one. So what is there about it? Okay, there's a lot of text here, but basically, so the question is what's mathematically, the function that represents pi? And in order to get there, what we want is to describe what we know about the system in a way that is maximally non-committal. Okay, so what we want is to describe the problem with what we know, the constraints, and what we want is to maximize our ignorance. And what is our ignorance? Okay, our ignorance is quantified by the entropy of the system. So we can actually solve this completely by simply saying that we want to maximize our ignorance. Okay, we want to be maximally non-committal. Okay, but we want to use the constraint we know, and the constraint we know is that the mean is 4.5. Okay, so I can just use this equation here, this set of equations, and I can solve for this. Okay, and I'm going to do this for you now. Okay, so basically this is what we want to do. Okay, we want to maximize our ignorance given some constraints. Our ignorance and information, I know in English they kind of like, they don't mean the same, but when we deal about with information theory, that is the same. Okay, so, okay, what is the function that I want to maximize here? It's entropy. So I want to write by that sum of p log p is the quantity that I want to maximize minus lambda. Okay, so I want the grad of this minus the grad of that of g, the constraints, and the constraint in this case is the mean, right? And so the mean, okay, the mean is going to be I pi. Okay, so that's my constraint. Okay, this is the equation that is set to 0. It turns out that I have another constraint. I have also the sum of the probabilities that is set to 1. I can add this constraint as well. And I can solve this, and this has to be equal to 0. Okay. I can rewrite this. I can take the derivatives. So I have to take a derivative with respect to pi. What does that mean? So here what I can do, I can think of pi, so it's a distribution. Okay, so I have I, and I have p values for I. And I can treat each of them as a different dimension, and I can take the derivative with respect to each of them. So I can do this d over pi of my entropy, okay, sum of p log p. All right, minus, and I'll continue later. So now if I just take the derivative with respect to pi, the sum over I doesn't matter anymore. Okay, so I can take the derivative for each I independently. Okay, and so this is going to give me d over dpi of pi log pi and the rest. Okay, let's try to derive to take the derivative here. I'm going to have log pi plus, let's see if I get this right. Okay, log pi plus, then I get the derivative of this is 1 over pi, so I'll get 1. Okay. And I'm going to have some other terms equals 0. Okay. In the other terms here, what I have is the constraints. Okay. I can show you the full derivation later because I'm running a bit out of time, but the solution to all of this, and that's very important, is that I get a distribution. So out of this, the unknown here is my distribution function. I get a distribution. And the distribution that I get, and I'm going to directly take the limit to continuous variables, okay, is that p of x is basically proportional to exponential of minus the constraints. Okay. And the constraint that I had was that the mean of some function of x was set to some number. Okay, so that can be the sum of the p's equals 1 or the mean of I equals 4.5. Okay. This is the key result. All right, so if I have a constraint, okay, on my random variable x, so f could be the identity. Okay, if it's the identity, it's a constraint on the mean. Okay, the mean of x equals a. Okay, then the solution, the maximum entropy distribution that is a solution to this problem is going to be exponential of minus x. Okay, what we saw here in this case, we saw at the end that we need some curvature. And actually now mathematically we know that the best guess solution to this problem is an exponential distribution. Okay, so this is an exponential that's rising. All right. I'm happy to go over the details with you later today if you're interested, but now let's look at different scenarios here. If the constraint on my variable is, okay, that's all I know about x. Okay, and I'm going to add also that x is not negative. Okay, then the distribution that will maximize the ignorance about everything else is p of x is going to be exponential of minus x over x0. Now I have a constraint on the variance. Okay, the solution to this is going to be p of x is exponential of minus x squared over sigma squared. And you find the Gaussian distribution. If I have a constraint on the mean and the variance, I can combine those two, and what I find, I will have a shifted Gaussian distribution. If I have a constraint on the geometric mean, okay, so let's say, okay, so this means that I have a constraint on the product of my variables. Okay, this is a constraint on the sum, and this is a constraint on the product. written with a log. Okay. Then can someone tell me what kind of distribution I get? Sorry? Yeah, x to the minus, and it's a different alpha, but it's just a normalization. Okay, so I get a power law distribution. Okay, so what is very interesting with this is that we now have a new language to talk about distributions. Okay, when you see a distribution, okay, usually it's loaded with math, okay, and it's hard to interpret. But what you can do is you can ask yourself, okay, so what are the maximum entropy constraints that will generate this distribution? Okay, and the constraints are very simple because the constraints are here, and this is much closer to English than the math that you can see with these distributions. Okay, so I will, by the way, all of this comes from Jaynes, and the maximum entropy principle is from 1957. This is shockingly recent. Okay, this is telling us how to think in the right way. Okay, how to make guesses in the best possible way. I find that shockingly recent in the history of science. And so he told us how to do that in the right way. There are all sorts of interesting connections to physics. I'm happy to discuss that with you later. I will just show you. Okay, this is a Wikipedia page. That's a page for maximum entropy distributions. And now what you can see here, this is the beginning of the lists, okay, of basically all the distributions that you encounter in physics and beyond. All right, so you will see the normal distribution, the chi-square, the Maxwell-Boltzmann, the Laplace, the exponential, etc., etc. Okay, and they come with all their complexity here. But what is very interesting to know is that they actually can be generated with very simple constraints. Okay, so what this says is the expectation value. Okay, so if I take the normal distribution, which is here, I can generate it just by saying that I have a constraint on the mean and I have a constraint on the variance. That's it. And the maximum entropy distribution, the solution of this, is just exponential of those constraints. Okay, and so this is a language that's much simpler than this one. And that allows you to understand distributions much better. Let's take an example for the astronomers in the room. Do you know about the Schechter function, the galaxy luminosity function? So how does it look like? What is the functional form? Sorry? Exactly. Okay, so the luminosity function, the number of galaxies of a certain luminosity goes like a power law and an exponential cutoff. Okay, so if I plot it here, I have log L, log phi. Okay, this distribution is like this. So one way to interpret this is the following. So we have a power law distribution here. Okay, I can generate that in a maximum entropy situation by saying that I have a constraint on the log of L. Okay, so that's a geometric mean. The geometric mean is describing things that grow multiplicatively. Okay, and so this is telling me that, the bigger you are, the faster you grow. Okay, the bigger of a galaxy you are, the faster you can accrete material around you, the more efficient you can do that. Okay, and so this is basically what is happening in this regime of the domain. And then we have an exponential cutoff. Okay, the exponential cutoff here comes from a constraint on the mean. The constraint on the mean is the same that's saying that there is a constraint on the sum of everything. Okay, and so this is about the finiteness of the universe. Okay, and so this is mostly finite in time. Okay, so galaxies have been able to grow up to a certain point only because the universe has a finite age. Okay, and therefore there is a finite extent to which one can grow and maximum value for the luminosity. And this gives rise to the exponential cutoff. There are many distributions in nature that have this form. And now you know where they come from. Okay? And so this gives you a new language to interpret distributions, and you can go back to all of your favorite distributions and try to understand what they mean instead of just seeing math. Okay, I should probably stop here. Is that right?
Yeah.
All right, so just to summarize, you can get these very interesting results thanks to entropy. Okay, so if you understand entropy, it opens up a whole new world. You can understand things with a new language. Okay, you have the language of constraints here. And what we will see is that for many machine learning techniques, we want to compare distributions. And so we are going to use the relative entropy or the KL divergence a lot. And so I'm doing all of this so you have the basis to understand one of these key tools that is used in machine learning to compare distribution and make inference. All right? I'll be happy to take all your questions during the coffee break. Thank you.